Have you ever really thought about it, that invisible superhighway, the one connecting some far-off power plant right to your coffee maker? It's this massive, globe-spanning system, right? And it literally powers our entire world. But what's wild is that it all kicked off with just a single spark of genius way back in the 19th century. So today, we're going to trace that journey. We're going to see how one simple discovery ended up electrifying, well, everything.
Okay, so our story kicks off with something that, I gotta say, looks a whole lot like magic. Check this out. It's an induction cooktop. You can put a pot of water on it, and bam, in just a few minutes, it's at a full rolling boil. But here's the crazy part. If you were to touch the glass surface, like right next to the pot, it's cool. I mean, totally cool to the touch. The surface itself isn't getting hot at all. So that leads to a pretty big question, right? If the stove isn't hot, how on earth is it cooking the food? I mean, where is that energy to boil all that water actually coming from? It kind of feels like it breaks the rules of, well, everything.
Well, the secret isn't heat. It's something you can't even see. Magnetism. Yeah, you heard that right. We're about to find out how you can literally cook with magnets.
So here's the deal. Underneath that glass, there are these hidden coils, and they create a super rapidly changing magnetic field. Now, this field, it just passes right through the glass, no problem, and it induces an electric current directly inside the metal of the pot itself. It's the pot's own resistance to that current that creates all the heat. So get this, the pot literally becomes its own burner, while the stovetop just stays cool. It's a crazy, direct, and super efficient way to move energy around. You know, this whole modern magic trick is really based on a question that scientists were obsessed with back in the early 1800s. See, they already knew that if you run electricity through a wire, you get a magnetic field. That was old news. The big question was, could you do it the other way around? Could a magnet, just a plain old magnet, actually create an electric current? Well, the guy who finally cracked that puzzle was a self-taught English scientist named Michael Faraday. And let me tell you, his discovery didn't just answer the question, it completely changed the course of history. And what's so amazing about Faraday is that he didn't come from some fancy university. He wasn't formally trained at all. He started out as a bookbinder's apprentice. He literally taught himself by reading the very books he was supposed to be stitching together. His curiosity was just off the charts. And then in 1831, he had his big aha moment. And this, right here, is the key idea: electromagnetic induction. It's basically making electricity with magnets. But, and this is the absolute genius of Faraday's insight, it's all about one little word: changing. A static magnetic field, one that's just sitting there next to a wire, does absolutely nothing. The magnetic field has to be changing. It has to be moving or getting stronger and weaker for any of this to work. That one word, changing, is everything. And his famous experiment illustrates this perfectly. Look at this. He took a simple iron ring and wrapped two totally separate, unconnected coils of wire around it. Now watch. When he flipped the switch on that first coil, creating a magnetic field, the little meter on the second coil jumped for just a split second. And then, nothing. It went right back to zero. But then, when he switched the power off, collapsing the magnetic field, the needle jumped again, this time in the opposite direction. He proved it. The electricity was only created in those brief moments of change.
So, and this is super important, Faraday didn't just stumble upon this effect. He figured out how to control it, how to dial it up or down. You want more current? Easy. Just coil the wire up, add more loops to that coil, or change the magnetic field even faster. Or, hey, just use a stronger magnet. This ability to actually control the outcome, that's what turns it from a cool science experiment into something incredibly, incredibly useful.
And this idea of control, it leads us straight to what is probably the single most important application of Faraday's law, a device you've definitely heard of called the transformer. Oh yeah, you use this tech constantly, every single day. You know that little blocky thing that charges your phone or the power brick for your laptop? Yup. At its core, that's just a tiny modern transformer. It's using Faraday's discovery to change the electricity from your wall into something your device can actually handle. So just think of a transformer as a souped-up version of Faraday's original iron ring. You've still got two coils of wire, a primary and a secondary, and they share a magnetic field. But the real trick, the genius of the whole thing, is just in how many loops or windings you put in each of those coils. And the rule here is just beautifully simple. If that second coil has more loops than the first one, the voltage gets stepped up. it increases. If it has fewer loops, the voltage gets stepped down. Simple as that. But, and this is a big but, there's always a trade-off. You can't just create energy out of thin air. So when the voltage goes up, something else, the current, has to go down. And when voltage goes down, current goes up. It's like a seesaw. And believe me, that trade-off is the key to our entire modern world. Okay, so we can change voltage up and down whenever we want. Cool. But so what? Why is that one ability so fundamentally important that we've literally built our entire civilization on top of it? Well, it all comes down to solving one enormous, headache-inducing engineering problem. How do you get massive amounts of electricity from point A to point B, we're talking hundreds of miles, without losing most of it before it even gets there? The big problem is something called resistance. Every wire has it, and trying to push a lot of electric current through that wire is kind of like trying to shove a whole river's worth of water through a tiny garden hose. You're going to get a ton of friction, right? Well, in electricity, that friction escapes as wasted heat. And the more current you push, the more power you just lose. And it's not a little bit, it's a lot. Okay, let's put some real numbers on this. If you just tried to send power from a typical power plant the normal way with high current, you would lose an absolutely staggering 90 megawatts of power. That is almost a third of the plant's total output, just gone. Poof, vanished into the air as useless heat. I mean, can you imagine? It would be a complete disaster, environmentally and economically. But here comes the transformer to the rescue. Remember that seesaw? Using a step-up transformer right at the power plant, we can crank the voltage way, way, way up. And what happens when voltage goes up? The current drops way, way down. By doing that one thing, the power loss to heat absolutely plummets, all the way down to less than 1 megawatt. We're delivering the same amount of power, but we're doing it with over 99% efficiency. This one simple trick, it's the only reason long-distance power grids are even possible. All right, so let's put it all together. Let's follow the entire journey of electricity and see how this transformer trick gets used over and over again, from the second power is created all the way to the outlet in your wall. So when you look at the electrical grid, don't just see a bunch of wires. It's really a massive, strategically designed system of transformers. It's this beautiful cascade of stepping the voltage up for the long haul and then carefully stepping it back down, with each transformer placed in the perfect spot to do its job. Okay, so here's the trip. It all starts at the power plant. Electricity gets generated at about 20,000 volts. Right away, boom, it hits a huge step-up transformer and gets boosted to over 230,000 volts. That's for the big cross-country journey on those massive transmission lines. Then, once it gets to your city, a substation steps it down to a more manageable level for zipping around the region. And finally, you know that green metal box you see in your neighborhood? That's the last transformer in the chain. It steps the power down one last time to the safe 240 volts that actually comes into your house. So think about that. Every single time you flip a light switch or plug in your phone or make a piece of toast, you are the finish line. You're completing this incredible continent-spanning journey. A journey that's only possible, only efficient, because of a simple principle that Michael Faraday figured out with a ring of iron and some wire way back in 1831. So yeah, that induction cooktop we started with, it's not magic at all. It's just really, really clever physics. In Faraday's law, it's not just for cooking. It powers our homes, our cities, our entire digital world. It's the perfect example of how one single, fundamental idea can completely reshape everything. And as we start looking to the future, with things like electric cars and new kinds of power plants, the question isn't if we're going to use this principle, it's how we're going to adapt it. So what do you think? What are we going to power with it next?